Welcome to Lecture 2.6, Mixing Problems. This is an application especially relevant to chemical engineering, though it certainly appears in other areas of science and engineering. And when I've given surveys at the end of differential equations classes and asking students what their favorite part was, I've had a lot of students say that the mixing problems were their favorite. Okay, so what are these problems all about? Here's an example. Let's suppose we have a tank of fresh water. So I'm going to sketch what this might look like. A tank of fresh water looks something like this. And we start out with some amount of water in it. Now, salt water flows in at some rate. So let's suppose that we have some pipe up here, and salt water is flowing in at some rate. Once the water is in the tank, we assume that this is fully mixed. And then there's some drainage pipe. And the water flows out of the tank at the same rate. Okay. So the question we want to know is, what is the concentration of salt in the tank at time t? Or alternatively, we could ask, how much salt is there in the tank at time t? So to do this, let's let x of t equal the number of ounces of salt in the tank at time t. So if we can figure out what x of t is, then the concentration, let's just call it concentration of t, is x of t divided by the volume of the tank, the volume of the water in the tank at time t. And in this case, it's constant because our rate in is equal to our rate out. Now, this is just an example problem statement. We can change a lot of these things. This rate in does not have to be constant. We don't need to start with a tank of fresh water. We can assume that we already have some sort of salt water. We're always going to assume that the water in the tank is fully mixed. That's one thing that's not going to change. But we don't have to assume that the water is draining out of the tank at the same rate. So we'll see some more advanced problems where the tank is actually filling up or draining. So I said this is a tank. It doesn't have to be a tank. It might, in real life, it might be something like a lake. This is a lake, and there might be a lake of fresh water, and this might be a river upstream, and there might be a chemical plant on the river that is dumping some sort of chemicals in the lake. And then this is a river that exits the lake, or that goes out of it, and the water that exits is, we're assuming that the chemicals get put in the lake and it's fully mixed up. And then we want to know when is the lake above, or when is the pollution in the lake above some threshold. Okay, so let's do an actual problem with actual numbers. So now suppose we have a tank that contains 150 gallons of fresh water. Suppose that the water that comes in is salt water with a concentration of 2 ounces per gallon, and it flows in at 3 gallons a minute. And let's assume that the water in the tank is fully mixed and the water drains out at the same rate. Okay, so the first thing to do every single time is let x of t be the amount of salt in the tank at time t, whatever your units are. Then x prime of t, this is the rate of change of salt, is the rate in minus the rate out. And again, not the rate of the water coming in, the actual rate of the salt coming in. So let me draw a picture of this. So we have a tank like this. We have a pipe that is letting water in at 3 gallons per minute and with a concentration of 2 ounces per gallon. We have water that is leaving at the same rate, so 3 gallons per minute. We are initially starting with 150 gallons. Actually, that's not going to change because our rate in is equal to our rate out. So, given this, let's follow this step. Let's first find the rate in. So the rate in is, so here's what I always like to do. I like to write this down, and even to this day, I will write down volume rate times the concentration. And by the volume rate, I guess it's my own little term, but I mean whatever this is. So in this case, this is going to be 3 gallons per minute, and the concentration of salt is 2 ounces per gallon. And remember from high school science that the units will cancel. Otherwise, you've done something wrong. And so we get 6 ounces of salt per minute are entering the tank. So the rate out, I'm going to write the same thing. It's the volume rate times the concentration. So the volume rate out is same as the rate in, so it's 3 gallons per minute. Now the concentration is a little trickier because it's not 2 ounces per gallon anymore, right? What is it? So the concentration of the water exiting the tank is just the concentration of the water in the tank, and that's going to be the amount of salt in the tank divided by the volume. So that's going to be X of T ounces of salt divided by 150 gallons. So as before, these units are going to cancel, and what we get is let me see, that's 1/50 times X of T ounces per minute. So now let's write a differential equation whose solution gives us the X of T that we're looking for. So X prime equals rate in, which is 6, minus rate out, which is 1/50 X. That is a differential equation. That's something we know how to solve. What does that remind you of? Well, it's your exponential decay to a value, because if you get rid of the 6, you just have an exponential decay. So this is something that we can solve. Actually, I should add one more thing. This is just a differential equation, but we actually know an initial condition. We say we have a tank containing 150 gallons of fresh water. So that means that at time equals 0, we have no salt in the tank. So we also have the initial condition, X of 0 equals 0. Okay, so let's solve this differential equation that we derived on the last slide. So that was X prime equals 6 minus 1/50 X. Let me box that. And we also had an initial condition, X of 0 equals 0, but I don't want to worry about that for now. So to solve this, we've actually seen 4 different ways, 4 different methods we can use. We can use the separation of variables. We can use integrating factor. We can use the variation of parameters. Or we can use that last method, that shortcut, I'm going to give it a name now, which I did not before. I'm going to call it undetermined coefficients. Because, and this is something that I call the y of t equals yh of t. So solve the homogeneous first and then guess a particular solution. I'm calling it undetermined coefficients because that's the name that's given to it when you'll see it in the next chapter when we study second order differential equations. But for now I've been calling it the shortcut, homogeneous plus particular. But remember that when guessing a particular solution, you guessed a general form with some constant a or a and b, and you had to figure out what those mystery coefficients were, hence the name. Okay, so let's use this last method because it's easier. So the homogeneous equation is x prime equals negative 1/50th x. Remember, we just get rid of this term that doesn't have an x in it. And the solution to this is exponential decay, so it's c e to the minus 1/50th t. Okay, so let's find a particular solution. And the first thing to do is to look for, is there a constant solution? So if there's a constant solution, that means that its derivative is 0, so let's set this equal to 0 and then solve for x. And you should be able to see that that's something that we can do. So let's find a constant or a steady state solution. So set x prime equal to 0, and then we have 0 equals 6 minus 1/50th x, and we can solve for x. We get x equals 300. Let's call that xp. So now we have the general solution, which is x of t equals xh of t plus xp of t, which is c e to the minus 150 t plus 300. So there is our general solution. And let's pause now to draw a picture of the tank and see what that represents. So recall we had that tank. We had a pipe coming in, pipe coming out. So we had water in here. We had water coming out at 3 gallons a minute. We had water coming in at 3 gallons per minute, and 2 ounces of salt per gallon. So the general solution does not involve the initial condition. So before I specify how much salt is in the tank, this is the differential equation that governs how much salt we have. Again, before we know how much we start with. So just given the information that it goes out at 3, in at 3, with this concentration. So let's solve the particular solution to this initial value problem. Remember, that's the equation plus the initial condition. So let's plug in x of 0 equals 0. Or let's plug in the initial condition. Let me call it that. Plug in the initial condition. So x of 0, so plugging in 0 in for t, we get c plus 300. C plus 300, and that equals 0. Remember, we set it equal to 0. So we get that c equals negative 300. So now the final solution to the initial value problem, sometimes we say the particular solution to the initial value problem, because it's not a family of solutions anymore, it's one and only one solution. It is 300 minus 300 e to the minus 1/50th t. And let me box that. Okay, so let me say a couple things about that. So we looked for a constant solution by setting this equal to 0, and we found that 300 was a constant solution. But let's see if we could come up with that without knowing any math, or not knowing much math, just purely looking at the situation. So what situation, how do I want to say this? So x of t is the amount of salt in the tank at time t. And how could it happen that that is constant for all time t? That's what we got. We got a constant solution. That's going to happen if the water that's in the tank originally has the same concentration as the water coming in, right? In other words, if this 150 gallons of water has concentration has salt concentration 2 ounces per gallon. And that happens precisely when, let's organize, so that happens, so x of t equals 300, that happens precisely when our initial condition, when the concentration is 2 ounces per gallon, meaning there's 300 ounces of salt in there. So when there's 300 ounces of salt in the tank originally, we get a constant solution. X of t is 300 because the concentration of the incoming water is equal to the concentration of the tank. And you can see that that is yeah, well, let me stop there. Let me say one more thing, actually. What is the limiting value of the amount of salt? So what is... Oh, let me move that. I'll do it up here. I'll use red. So what is the limit as t goes to infinity of the amount of salt in the tank? That is... Well, that's the limit of this as time goes to infinity. So what happens when you plug in a really large t? Well, this term goes away, and you're left with 300. This is what remains. So that's going to be 300. And that is, in fact, the constant solution that we found. And let's make sure that this makes sense. So now after 10 days, we start with fresh water. Or actually, it doesn't matter what we start with. We can start with fresh water. We can start with something that's super concentrated. It doesn't matter. Whatever we start with, after 10 days, assuming that we have water coming in with 2 ounces per gallon concentration, that's fully mixed and it's draining, that the concentration of this water is going to approach 2 ounces per gallon. In other words, the salt content is going to approach 300 ounces. And that's exactly what we get by taking the limit of this as time goes to infinity. Finally, let me say one more thing, because I think I actually asked for the concentration at time t, not just the amount of salt. So let me say that the concentration at time t is, let's call it c of t. That's just x of t, the amount of salt, over the volume, which is 150. So that's 2 minus 2 e to the minus 1/50th t, and you can see that as time goes infinity, the concentration will approach 2, which is the concentration of the incoming water. Okay, so next time we're going to make this a little more complicated. We're going to do an example where the incoming rate and the outcoming rate are different, and that's going to be harder because the volume is no longer going to be constant. So this equation is going to have a t in it. And we're also going to see an example where we have two tanks, where we have one tank that drains into another tank that drains out. You can think of this as one lake feeding into another lake. And in that case, we're going to get a system of differential equations, which in general is going to be hard to solve. We need some more techniques, although in the simple case, it's something that we can do. And solving general systems is going to be the subject of the Chapter 4 lectures.